Hey, I wanted to talk to you about Isaac Newton. He lived about 400 years ago in the very realm of Bach and the organ that you just heard and everything. So, interesting guy. Let me tell you a little bit about him before we get started here. Lived 1643 to 1727. Look at all the stuff he created there. He single-handedly invented calculus and a ton of physics. He was interested in chemistry and alchemy and religion, theology, mathematics, astronomy, everything. He was the head of coinage in Great Britain, making sure the coins came out right. You name it, he had his hands in it. And so much of what we do in physics comes back to this guy that we kind of sometimes call this Newtonian physics or, classical physics. But we're kind of moving here, changing horses. We were talking about kinematics, how an object moves, the x, v, v naught, a, t, all that stuff. We want to switch over to think about why it moves, and we call that dynamics. So that's the new topic for today. You've heard of Newton's three laws, and probably since middle school or elementary school, maybe somewhere way back there. No real surprise here. The first law says, in an inertial frame of reference, an object either remains at rest or continues to move at constant velocity unless acted upon by a force. Maybe they phrased it a little bit differently, but the idea is the same. A box that's just sitting here is going to sit there until somebody comes along and puts a force on it, right? If it is at rest, it will remain at rest until acted upon by a force. All right? That's kind of the critical part there. I don't think there's any big surprise about that. Here's another possibility. It continues to move at constant velocity. If I had a box that was moving, why, it would keep moving until something stopped it. That something might be friction. It might be it hits the wall. It might be that runs into something, whatever. But if an object is at rest, it will stay at rest. If an object is in motion, it will stay in motion until something acts upon it. We talk about inertia being a property of matter that makes this one to happen. It wants to continue in a straight line. So that's a term that gets tossed around. Here's Newton's second law. In an inertial frame of reference, there's that phrase again. You don't really need to worry too much about what that means right now. But what we're interested in is when I do put a force on an object, that force is equal to the mass of the object times the acceleration of the object. And this is kind of the main formula of test 2 are those three little letters right there. Let me just show you real quick how this works. If this is a box, it's something that has mass, and we need to define mass here a little bit better in just a second, but let's say the mass is 4 kilograms. Okay, 4 kilograms of mass would be about 8-9 pounds of weight. So mass is a way to measure how much stuff something has. How much matter, how many atoms and molecules, and how much all of that adds up to together. Okay, if I come along and put a force on this thing, I moved it. Did you see that? Okay, so here is a force F, and we could talk about how it accelerates. The acceleration might be 2 meters per second squared. You can see how easy this is to do. The mass was 4 kilograms. And the acceleration is 2 meters per second squared. 4 times 2 is 8. Normally we would say that's 8 kilogram meter per second squared, except that seems like a lot to write. And so we just write 8N, where N is short for Newton. And 1 Newton equals 1 kilogram meter per second squared. All right, so you can just kind of replace that and abbreviate it down, if you will, like that. But that's going to be the heart and soul of what we do right here. This guy is immensely important. If you have more than one force, then you need to get the sum. You need to add up all the forces. So we'll see some of those, all right? But it's going to come back to that right there. Here's the third law. Whoops, we got a couple examples. I just did an example for you. Oh well. Let's do the second one. This is pretty much the problem we just did. We had 4 kilograms and 2 meters per second. But 8 Newton force accelerates a box at 2 meters per second squared. It's just like kinematics. You come through and you get your variables. You say, let's see, I got an 8 Newton force. Oh yeah, Newton's measures force. So F equals 8 Newtons. I got this number right here in meter per second squared. And of course we recognize the unit meter per second squared to be an acceleration. So since everything in this test comes back to F equals ma, and I've got F and I've got A, and I'm looking for the mass, see how that's a good formula to use right there? I could even go ahead and solve it for mass, all right? Force divided by the acceleration would be equal to the mass. And then I can put my numbers in there. 8 newtons divided by 2 meters per second squared equals the mass. 8 divided by 2 is going to be 4 kilograms. And we're done. Okay? So nothing terribly picky about, tricky or hard about doing these problems. If there's only one force, you use F equals ma and you're done. Okay? Easy. If you have more than one force, you need to be a little bit more careful. And what I'd like you to always get in the habit of doing anytime you see anything about forces, if a physics problem has forces in it, you need to come along and draw a picture. Okay? There's a box. All right? I'm looking for the numbers like always, so I see that 8 kilogram box, and kilograms measures mass. So I would put 8 kilograms of mass right there. All right? And then I'd come in here and look at the rest of this. Here's a force right here, force A, force B, force C. That's 3 different forces. It's not just a single force this time. I've got multiple forces. I need to understand what those forces are and which way they point. So to help me do that, I'm going to draw a little picture down here. Nothing hard about this at all. But you want to say, let's see, I've got a 4 Newton force that's pushing to the east. East, we'll let that be to the right. So I'm going to call this F sub A, 4 newtons east. The next one here is 12 newtons to the east. So I'd come in and draw an arrow. Now if you want to make a bigger arrow, that's fine. This is a bigger force, so you know the length of that arrow could kind of represent a longer, bigger force there. But see how they both point to the right? They both point east. They're in the same direction. So I got to make sure that I've got that down. This last one here, though, is west. 8 newtons west. That points the opposite direction. So I need to draw an arrow that points to the left in the opposite direction. That's F sub C equals 8 newtons west. All right? You have to draw that picture right there so that you can see how many forces there are, what they are, and which direction they point. There are 2 names that people call that. The simple one is a force diagram. So that works fine. It's a little bit fancier. I'm not really sure where this name comes from, but a free body diagram. Like that. Okay? So I have drawn the force diagram, or the free body diagram, and I've got all the forces that they mention in the problem. Now there's actually 2 more forces that we probably should put on our picture here. So let me put those ones on, and then we'll talk about how much we need to put those on every time or not. Gravity is going to pull down on this thing. and then this thing is sitting on the ground or sitting on a table or sitting on something. So the table, let's say, is pushing up. Technically, those are forces on the object, so they should be on the free body diagram. And we have 5 forces to deal with now. All right. So this is a two-dimensional problem. I've got things that are acting in the y direction, and I've got things that are happening in the x direction. And remember how I told you if you have a two-dimensional problem, you need to separate it out and say what's happening in x, what's happening in y. Well, that applies here too. So it would be okay to say, let's think about the y direction. And I want to use Newton's law here, except remember when I have more than one force, we really kind of put a sigma out front here. That sigma starts with S, as does sum. So this would be read, the sum of the forces equals the mass times the acceleration. And I want to write that down for every problem. The sum of the forces equals mass times acceleration. Now in this case, I'm only talking about the y direction. So it makes sense to come in here and say the sum of the forces in the y direction equal the mass times the acceleration in the y direction. And now I've got a starting place. This is going to be the starting place for every problem you do on test 2. Okay? You have to look at your picture and you have to say, well, what are the forces? And then you add them up, set it equal to mass times acceleration. I only want the y direction forces here. The table pushes up and gravity is acting down. And I'd have my equation. Okay? It's that easy. Now, there's a fancy name for the table force. Anytime the ground or the table or whatever pushes up, we call that F sub n, which is short for the normal force. And it doesn't mean that it's normal that the table pushes up. We're using the mathematical sense of normal, which means perpendicular. The normal force will be perpendicular. The table pushes straight up on the box. All right, so if you want, you could come in here and say this is F sub n. To calculate the gravity, that's mg, the weight of the box. And I've got a little bit more about that at the end. So we could write that. Replace gravity with mg. The mass of the box, it's 8 kilograms times 9.8 meters per second squared. Over here I've got mass times acceleration, but an interesting thing happens. That box is not floating off into the air and it's not sinking into the ground. The acceleration in the y direction is equal to 0. So m times 0 is 0, and I would just get this. And it doesn't take a whole lot of algebra to realize that the normal force is going to equal the weight of the box. They're going to cancel each other out. The gravity pulls down, and that is perfectly canceled out by the normal force pushing up. So it doesn't go up and it doesn't go down. Nothing happens in the y direction. I don't know how interesting you find that. I don't know how many times you want to work that out. But in general, I don't put those two forces on the picture unless there's some more forces in the y direction. And then you do have to think about it. But most of the time you can leave those two off. All right, so I'll put them in the picture. We did the equation. It worked out fine. Nothing happens that way. Boring. Okay? So let's see what's going on in the x direction. That promises to be a little more interesting. In the x direction, I always start off right here. The sum of the forces is equal to mass times acceleration. The x's tell me I'm only thinking about the x direction forces. So I'm only looking for forces in the x direction. I see this blue arrow. I see the green arrow. Those both point to the right. So I'm going to call that the positive direction. And then back over here I've got this black arrow which is pointing the opposite direction. So it gets a negative sign. And it would look like this. I'd have F sub A plus F sub B minus F sub C equals M A sub X. I'm just copying the right-hand side. But on the left, I'm making a list of the forces in the x direction. I see 3 forces that push sideways. 2 of them push to the right, 1 to the left. I write them down. I got to get my signs right. I'm thinking about a coordinate system here, and it doesn't ever hurt to draw that coordinate system in. And you could just come along in here and say, I'm going to draw a coordinate system, and doesn't really matter which way you pick again. Either way works. But you know what? I see that I got two forces, 4 and 12. That's 16. That's going to beat out the 8. So I'm expecting this thing to move to the right. Generally, if you can call the direction of motion positive, that makes more sense. Okay? But you could do it the other way if you wanted to. These two push to the right. To the right is positive. So this guy's positive and that guy's positive. F sub c points to the left. He gets a negative sign because he's the opposite direction. All right. We're looking for the acceleration right here. So I'm going to try to annex a little bit of extra space off here and bring this over. If I were to divide both sides by m, then the m's would cancel on the right, and I'd have that a sub x all by itself right there. And that's what we're looking for. Okay. Over here, f sub a is a positive 4. F sub b is a positive 12. F sub c, negative because it's to the left, 8 newtons. And I want to divide all of that by the mass, which was 8 kilograms. Right here I'm going to have 4 plus 12 would be 16 minus 8 would be 8. And then divide that by 8. I end up with 1. This was newtons plus newtons minus newtons. That's newtons on the top. And kilograms on the bottom. That's supposed to be my acceleration. That doesn't look like any units of acceleration I've ever seen, except it doesn't hurt to remember that a newton is really a kilogram meter per second squared. And when I divide that by a kilogram, the kilogram on the top cancels the kilogram on the bottom, and there's my acceleration in meters per second squared like we like to see. All right. So that's a problem that we could do right there. Two-dimensional problem, break it into 2 dimensions. What's happening in the x direction, what's happening in the y. They have nothing to do with each other. All right. And you're always, always, always going to start with the sum of the forces is equal to mass times acceleration. In order to build this equation, you have to have the force diagram to say, well, I've got 2 arrows that I need to add in the y direction, and I've got 3 arrows that act in the x direction, and make all that happen. All right? Great. What I got to do here? Here we go. Here's a little problem. This is Newton's third law, rather. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude, opposite in direction on the first body. You've heard that said other ways. Every action has an equal and opposite reaction. Every force has an equal and opposite force in the opposite direction. Whatever. Okay? So that's fine. There's no formula there. There's nothing we're going to really do with that. So thank you, Mr. Newton. We appreciate it. The second law is the one we're going to zoom in on. And here's a little bit more that I promised you about mass and weight. I've already told you that mass is a measurement of how much matter, how much stuff you have. Atoms have mass. We measure that mass in kilograms, so that would be the unit. Weight, on the other hand, over here, would be how much gravity pulls on matter. So that's kind of a different animal there. Not quite the same thing. These two are related, but they're not the same thing. If I pick up a pencil sharpener here on Earth, it has mass, right? It's got matter to it, and I could add that up and get a number to say how much mass are we talking about. That mass will be less than the mass of a refrigerator. The mass of the pencil sharpener will be greater than the mass of a paper clip. All right. It will also have a weight because I'm here on Earth. Earth's gravity is pulling down on the pencil sharpener, and I have weight. So I'd have both here. Not the same number, not even the same units. This weight is a force. It's the force of gravity. So that would be measured in newtons in physics. In everyday America, we would measure that in pounds of weight. So when you jump on the scale, bathroom scale, you're taking your weight, you're measuring your weight. We don't really do anything with mass in this country other than physics. So it's kind of a unique thing. We do not have a unit for mass in this country, not one that we use anyway. If you do need one, it's called slugs, but nobody really works in slugs that I know of. So there is one, but we don't really use it. We like kilograms of mass and newtons of force because those are the metric units. These others are imperial units, American units, British units, whatever you want to call them. ASE, something like that. Okay, but do you see the difference there? If I take that pencil sharpener, which has both mass and weight on Earth, and I take it out into space, away from Earth's gravitational field, it still has every atom, every molecule, every gram of mass, every kilogram of mass, but there's no weight because gravity is no longer pulling on it. They're related, they're not the same. Anytime you want to go from one to the other, you'd say the weight equals mass times gravity. All right? That gravity is going to pull down. So anytime you see something and it says here's a 4 kilogram box, if you're on Earth, then you need to go ahead and start thinking about that mg, unless it's sitting on a table and the table pushes up with that normal force we talked about, and these will cancel. Okay, so we'll see some more of that in the next video, but that's Newton's second law. It's all of his laws, but second law is the important one, the one that we work with so often. Thank you.